So first and foremost, we were on a hiatus because of our grade 12 semester 3 exams, and we took a break.
Yeah. One of us was studying really hard, and the other was, well, you can say, half studying, but still studying something.
Yeah, whatever. We don't talk about it. But so, like, I was ready to record, like, the whole time, especially after our five exams in 5 days, and then Friday, Saturday, Sunday for math. We had the break, so I was ready to record. Then you just didn't record.
Yeah, fine. Put all the blame on me. Good.
No, I'm just saying. Anyways, let's go to the topic though. Encryption. Okay. So at this very moment, there are many countries and many people that are storing a lot of encrypted data like passwords, bank details, and social security numbers.
But wait, they can't open these files, so why are they doing it?
Well, that's because they believe that within the next 10 to 20 years...
A bit beliefs and truths and all. What is this, TOK?
No, it's just they believe or whatever think that in these next 10 to 20 years, they'll have access to a quantum computer that can break that encrypted data like passwords and all that in the future. So it's called Store Now, Decrypt Later, or SNDL. And it works because there's information around today that will still be valuable in a decade. Like, for example, things like research, like industrial and pharmaceutical research.
Yeah, top secret Elon Musk dancing footage.
Yeah, and little government intelligence. And everyone's aware of the threat.
The US National Security Administration says that a sufficiently large quantum computer, if built, would be capable of undermining all widely deployed public key algorithms.
Oh, our current encryption standards like RSA and ECC and the Diffie-Hellman key exchange have been like very successful, and they've been working like for the last 40 years very nicely. And this is also constantly the topic of my math EE, so I know a lot about it.
Yeah.
But let's go back a couple of years for the history of it.
Yeah, okay. So up until the 1970s, if you wanted to exchange private information with someone, you would first have to meet up with the person, like meet up with them in person and share a secret key, as we say. This same key would be used to encrypt and decrypt messages. So it's known as a symmetric key algorithm. And as long as no one else gets their hands on your key, your messages are safe.
Yeah. But now what if you want to send information to someone that you've never met? And it's too hard to arrange an in-person meeting. So you can't really send a key over an unsecured channel because then they'll get the key and then the message is no longer encrypted. So in 1997, that fact led three scientists, Rivest, Shamir and Adelman, to come up with an encryption breakthrough, and it's today known as RSA, as what I just said like a couple of minutes ago, that RSA. So that Rivest, Shamir and Adelman, that led to they led to the creation of the RSA algorithm.
And it works something like this. So every person has two really big prime numbers, all their own, which they keep secret, okay? And they multiply these numbers together to get an even bigger number, which they make public for everybody to see. Okay. Now, if I want to send someone a private message, I use their big number to encrypt, or so I can say to jumble up my message. Correct? And I jumble it in such a way that it is impossible to unjumble it without knowing the two prime factors that made that number. This is an asymmetric key system since different keys are used to encrypt and decrypt the message. So it's easy for my intended recipient to decode, but impossible for everybody else unless they can factor that extremely large prime number.
Yeah, and now someone can try to factor it, right? Using like a supercomputer.
Yeah.
But in the best known factoring algorithm, the general number field sieve, modern cryptography can't, it doesn't happen, okay? It's just, because modern cryptography uses prime numbers that are around 313 digits long, and factoring this kind of product of two primes that's this big, even with a supercomputer, takes around like 16 million years. So it's not it's not that big of a problem in this day and age.
Yeah, but this brings us to the fact that cryptography or encryption or whatever you want to call it, isn't really an unbreakable lock that will keep your data safe forever.
Yeah, right.
It's just a big, almost unscalable barrier that it's not worth it to even try. But that's not the case for something called a quantum computer,
which we've spoken about in earlier episodes.
Yeah. So in normal computers, a bit, which is like a fundamental particle of the computer, it can only be in one state at a time. So either a 0 or a 1. So if you had 2 bits, they could be in one of 4 possible states, which is like 0, 0, 0, 1, 1, 0 and 1, 1.
So let's say each of these states represents a number like, so 0, 1, 2 and 3 are the same corresponding to the ones you just said, okay? So if you want to do a calculation, for example, raising 7 to the power of 1, like power of one of these numbers, as in like 7 to 0, 7 to 1, 7 to 2 and 7 to 3. So quantum computers can do this simultaneously rather than when a classical computer can do only one calculation at a time. Because as we said in, I think which episode was quantum computers? I think like 12, right? Yeah, okay. So unlike a classical bit, a qubit doesn't have to be in just one state at a time, like 0 or 1 is for a classical bit. It can be an arbitrary combination of both the states, or a superposition, if you will, of 0 and 1. So if you have two qubits, they can exist simultaneously in a superposition of 0, 1, 2 and 3 at the same time.
Yeah. And you like only come to know what the actual position of the state is once you measure it. It's related to the Schrodinger wave equation.
Yeah.
So when we repeat this same calculation,
like the calculation of 7 to the power of each of these numbers.
Yeah. It will actually perform the calculation for all of those numbers at the very same time. And what we're left with is a superposition of the 4 different answers which you get 1, 7, 49 and 343.
Right.
And if we add another qubit, we can double the number of possible states. So within 3 qubits, we can represent 8 states and thus perform 8 calculations all at once. So if we increase it to like say 20 qubits, you can already represent over 1 million different states.
Yeah, because you're doing 2 raised to 20, that's a lot.
Correct. And with 300 qubits, you can represent more states than there are particles in the observable universe.
That's just incredibly powerful.
It is.
But there's one very big catch. It's kind of like a random mixture, as you said. It's just a superposition of them. It's not actually an answer per se. We don't actually know 1, 7, 49 and 343 like separately. We just know that it's a mixture of them.
Correct.
Per se. Okay, it's like we can't actually identify each of them individually. So only when you make a measurement do you get a single value from the superposition, but it's at random. So you don't really know if you get 1, 7, 49 or 343.
And all of the other information is lost. Once you make that measurement, what you have is only that value that you get. Baki ka sab is gone.
So in order to actually harness and use a quantum computer properly, to actually use it to your advantage, you need a smart way to convert the superposition of states into one that contains only the information that you want to keep and removes the rest.
Yeah.
So instead of being random as it is right now.
Correct.
So this is a very difficult task, and that's why for most applications, quantum computers are practically useless.
And so far, we've only identified like a few problems where we can actually do this. But as luck would have it, these are precisely the problems that form the foundation of all the public key cryptography that we use today. So in 1994, Peter Shor...
Yes, the guy who made Shor's algorithm, that guy,
Yeah. And Don Coppersmith, both of these guys, they figured out how to make a quantum Fourier transform.
So it works basically like a normal Fourier transform. You apply it to some periodic signal and it returns the frequencies that are in that signal. But does this seem interesting, particularly? Not much, right? But consider this. If you have a superposition of states that's periodic, that's kind of like the terms in the superposition that they're separated, okay? By some regular amount, if the terms are separated by some regular amount, we can apply the quantum Fourier transform and we'll be left with the states that contain the frequency of the signal, which we can measure.
Yeah. And the quantum Fourier transform allows us to extract frequency information from a periodic superposition. And this is going to come in handy. So how does a quantum computer factor the product of two primes much faster than a conventional computer? And this is what we're going to find out in the next episode.
Adios, amigos.
Yeah, just kidding, just kidding. So this was becoming too long of an episode, so we decided to break it into 2 parts, and we'll give you some more to chew on before we get on to the next part.
Yeah. So let's say we have a number n, which is a product of 2 primes, p and q, and let's set n equal to 77. So I bet you can guess the prime factors.
Yeah, 7 and 11.
Yeah. But let's pretend for the moment we don't know them, because with the product of really big primes, we wouldn't really know them. So let's do a kind of a magic trick. Pick a number g that doesn't share any factors with n. And if you multiply g by itself over and over, you will always eventually reach a multiple of n plus 1. So like g raised to n no, g raised to whatever you raise it to, g raised to r, let's say,
Yeah.
plus 1 equal to n. So in other words, you'll always find some exponent r such that g to the power of r is a multiple of n plus 1. So pick any number that's smaller than 77.
Okay, so I'll pick like 8, and obviously this number doesn't share any factors with 77. And if you were doing this with big primes, it would also be extremely unlikely that you just happen to pick a number that shares factors with n. So you multiply 8 by itself once, twice, 3 times, 4 times, and so on, raising 8 to even higher powers, and then divide each of these numbers by 77. We're not really interested in how many times you multiply 8 by itself.
And then really something really marvelous happens, which you'll find out in the next episode, so keep a lookout for that. We love hearing from our listeners and are always excited to dive into new topics.
You can reach out to us on quarktalkofficial@gmail.com at any time.